Have you ever stopped to think about how the incredible worlds in your games actually come to life? I mean, how they go from just a bunch of data to a stunning 3D object on your screen. Well, it's not magic, and today we're going to peel back the curtain on the very first steps a computer takes to build everything you see. So, this is the central puzzle, right? At its core, any 3D model, a character, a car, anything, is really just a massive long list of numbers. Coordinates. So how does a graphics card take that digital blueprint and turn it into a solid object we can actually see and interact with? That's the journey we're about to go on. Let's think of this whole process like being a digital sculptor. Before you can even start shaping the clay, you need two things: the clay itself, your raw materials, and a plan. So let's take a look at the absolute basic ingredients of a 3D model. And the most fundamental ingredient, the absolute atom of the 3D world, is the vertex. That's it. It's just a single point in space with an X, a Y, and a Z coordinate. Seriously, every complex object you've ever seen in a game, from a hero's face to a giant spaceship, is built from thousands, sometimes millions, of these simple little points. So how does the computer keep track of all these points? Well, it cleverly uses two different lists. First, you have the vertex buffer. Think of this as your pile of raw materials. It has the data for every single point. But then you have the index buffer. And this is the game changer. It's the instruction manual. It just tells the GPU the order to connect the points, which means you don't have to store the data for the same point over and over again. It's a massive, massive win for efficiency. Okay, so we've got our materials and we've got our instructions. Now it's time for the first automated step in the process. A little component called the input assembler steps onto the scene, and its job is basically to be a data collector, gathering up everything it needs to start building. The input assembler's job is super straightforward and methodical. First, it reads those two lists, the vertex and index buffers, from memory. Then, using that index buffer as its guide, it grabs only the specific vertices it needs for a shape. And finally, it connects the dots, assembling them into basic shapes called primitives. And these are almost always triangles, because triangles are the simplest, most efficient 2D shape a computer can possibly work with. All right, our raw materials have been gathered and connected into a basic, raw form. Now, the artist steps in. This is where the real magic begins to happen, thanks to something called the Vertex processor, or as you've probably heard it called, the Vertex shader. The Vertex shader is this tiny but incredibly powerful bit of code that the GPU runs for every single point in the model. This is where developers get to be really creative. By writing custom code here, they can manipulate the math for each vertex to create all sorts of amazing effects, making water ripple, a flag wave realistically in the wind, or a character's skin stretch and bend as they move. But at its core, you really should think of the Vertex processor as a pure mathematician. It's not guessing or faking anything. It is performing precise calculations on every single point to figure out its exact position, its correct orientation, and its final size in the world. It's all just math. So our object now has its shape, but it's basically just floating in an empty void. We need to actually place it inside our game world. And that means taking it from its own little local space and transforming it into the global scene that we see. The very first step uses something called a model matrix. Just imagine that our 3D model was originally built at coordinate 0. The model matrix is the set of instructions that says, okay, now move this thing 10 units forward, rotate it 45 degrees, and scale it up to be twice as big. It's what puts the sculpture on its pedestal in exactly the right spot. Now, for a bit of a mind-bending trick, you'd think the next step is to move the camera to look at the object, right? Nope. The view matrix does something way cleverer. Instead of moving the camera, it moves the entire world around until the camera is sitting perfectly at the origin, at point 0, looking straight ahead. It's a bizarre-sounding mathematical shortcut that actually makes the next step way, way easier. Okay. With the whole world now perfectly positioned right in front of our stationary camera, the final transformation can happen. It's called the projection matrix. This is what creates that crucial illusion of depth. It acts just like a camera lens, defining your field of view and applying perspective, which is what makes things far away look smaller than things up close. It essentially squashes that 3D scene down onto a flat 2D plane, all ready to be drawn. So, that's a lot of technical stuff. I know. That's the how. But why does any of this actually matter to you?
Well, because the efficiency of these very first steps has a direct, tangible impact on the games you play every single day.
Seriously, think about it. You know when a game intentionally makes a distant mountain look less detailed? That's a level of detail system, or LOD, and it's designed to make the input assembler's job easier. That incredibly smooth animation when a character bends their elbow? That's the Vertex processor doing some really complex math. And most importantly, your frame rate, your FPS, is directly tied to how many of these vertices your GPU can possibly process every second.
So, if your game is ever running really slowly, there's a good chance it's what we call vertex bound. As you can see right here, loading a model with an insane number of vertices can absolutely crush your performance. Your GPU just can't keep up with the sheer volume of points it's being asked to calculate, and your frame rate plummets.
And here's a really fascinating little side effect of all this math. It all relies on numbers with decimal points. Now, if you place an object incredibly far away from the world's center, those numbers get so huge that the computer starts to lose precision. It starts making tiny rounding errors. And the result? The model starts to visibly shake or jitter on your screen. It's a really common glitch you've probably seen in huge open-world games. Ultimately, you have to remember that everything we've just discussed is the absolute foundation for what comes next. The next big stage is called rasterization. That's when the computer actually starts drawing the pixels. But it can only do its job correctly if these first few steps give it a perfect blueprint. If this stage is wrong, the whole image just falls apart.
So we've done it. We've taken a long list of numbers, we've assembled them into triangles, and we've positioned them perfectly in front of our virtual camera. All the points, all the vertices, are in their final 2D spots. But that just gives us the outline, the skeleton. The big question is still out there. How does the computer figure out how to color in the millions of pixels that lie between those points? Well, that is a story for the next part of the graphics pipeline.